So let's quickly review how we add fractions with the same denominator, and then we'll discuss how to add fractions with different denominators. Let's look at these first two examples. 2/3 plus 8/3 is 10 over 3. Notice the same common denominator out here, and the numerator is simply adding of 2 and 8. You see the same thing here. We are adding fractions with the same denominator of 5. The sum is also a fraction with the same denominator of 5. The numerator 14 is simply 3 plus 11. Now remember the whole story of this. How did we define addition of fractions? We said if you want to add two fractions, look at a segment of length 2/3 and attach to it another segment of length 8/3. 2/3 plus 8/3 is really the length of the long segment that we get from concatenating the segment of this length and a segment of length this. And that made total sense. And then we went ahead and said, well, then what would the answer be? What is really the length of the long segment? I understand concept-wise, this would represent the length of the long segment. The short segment of this length put together end to end with another segment of this length. And then we said 2/3 is 2 copies of it, 1/3. 8/3 is 8 copies of 1/3. So it's really when the long segment is 2 copies and another 8 copies of the same thing, which is 1/3. And that gave us 10 copies of 1/3. And here's how we got 10 over 3. That was the logic. And that was the same thing out here. Now let's look at this third example. 2/3 plus 3/5. What is this? How do we think of this addition? What's the definition of this addition? The concept-wise, it's still the same. As in, 2/3 means think of a segment of length 2/3. It can start at 0 and end at 2/3 on the number line. And then attach to it another segment of length 3/5. Then what do you get? You get a long segment whose length is 2/3 plus 3/5. So the long segment, you get it from concatenating a segment of length 2/3 with a segment of length 3/5. That means you took two short pieces, length segment of 2/3, and attached to it end to end another segment of 3/5. So there, the addition, it represents the length of the long segment. But you might say, I would like to have a fraction answer for this. And what is that? So let's talk about that now. So here we notice 2/3 is 2 copies of 1/3. Add to it 3/5. 3/5 is 3 copies of 1/5. So do you see what's going on? Why this problem is different from 1 or 2? Let's go back and look. Here what were we adding? We were adding copies of the same thing, meaning 2 copies of 1/3, 8 copies of 1/3 also. So we had the short pieces that we were adding up were all of the same length, 1/3 and 1/3 and two of those third pieces, 8 of those third pieces. So we could just count how many of those those third pieces we had. That's why we could just add the numerators 2 and n and 8 and get our 10. The problem we are facing here is we have 2 pieces of the length 1/3, and then we are adding to it 3 pieces of a different length of length 1/5. So there's no way we can simply say let's count them all together. So think of it on another situation like this. Say you have 2 pennies and 1 quarter. If I put them on the table, could you just count the coins as in 1, 2, 3 and say I have 3? You cannot, because 2 pennies, they are one time, they're pennies. A quarter is 25 cents. You have to convert it, but a quarter is not the same thing as a penny. We can't just count 1, 2, 3. We can't add on. They're not of the same value. We are facing the same problem here. Here what we're facing is we're trying to add 2 things, but they're not the same type. This is 2 copies of segments of length 1/3. This is 3 copies of segments that are 1/5. They're not of the same size pieces. So how do we do? So now what do we do? So just like in the 1 penny and 1 penny and quarter, how do we add it? Well, we think of a quarter as 25 cents or 25 pennies. So we're converting the pennies, the quarter into pennies, and then we can add and say 25 and add on 26, 27. Then we get 27 pennies. That's what we can do. So we want to use the same idea. These are 1/3 pieces. These are 1/5 pieces. We would like to convert them all into some other shorter piece. So they're all the same length. Then we can just count them just like we did out here. So how do we do that? So let's recall FFEF. Do you remember that? Fundamental fact about equivalent fractions. Let's go to the other board and review it. We'll review that quickly. Okay, here it is. So you've seen FFEF before, you've worked with it. So this should be a very quick review. So read along with me. A fraction is unchanged when we multiply its numerator and denominator by the same non-zero whole number. We can also write it symbolically using letters as follows, and you will see when we go back to adding fractions with unlike denominators, you will see why the symbolic notation is the most useful, because we directly use this and so on. So let's look at what I have here. I have a fraction a over b. A over b are letters, but really what are the letters? I write here a and b are whole numbers, and here, let me make a correction, that's b, okay? I do not want the denominator to be 0, because remember the denominator tells us how many pieces we cut up the unit segment into. The unit segment is already one piece. We cannot cut it up into 0 pieces. So the denominator of a fraction cannot be 0. So a and b are whole numbers with b not equal to 0. And here's a neat way of writing b not equal to 0. I put an equal sign and I just cross it out. So that's the shorthand mathematician's way of saying b not equal to 0. So let's go back to the symbolic notation. A over b is a fraction once you've picked your whole numbers. And what this is saying is it's unchanged, so equals. And what did I do? I got a second fraction, who's new from the first fraction. How did I get that? I took the a and b and I multiplied numerator and denominator by the same whole number. When I use the same letter n, that's how I indicate I'm multiplying by the same whole number. N is a whole number. Here I write n is a whole number. I also do not want the denominator to be 0 again, so n is not equal to 0. So we can multiply with any fraction. The moral of the story is, given any fraction, we somehow don't like the looks of it, go ahead and multiply both the numerator and the denominator by the same non-zero whole number. If you do that, no problem. The fraction you get is really not a new one. It is exactly equal to the old one. So let's go back to a problem with this knowledge at our fingertips and see what we can do. Okay, here's the problem we were looking at. 2/3 plus 3/5. Adding two fractions where the denominator is not the same. The issue we were facing was 2/3 is 2 copies of pieces that are of 1/3 length. Each piece is of 1/3 length. 3/5 is three copies of 1/5. So we couldn't just add them together as in counting. We can't add 2 and 3 because these are not two. The 2 denotes 2 copies of a certain thing, 1/3 pieces. 3 is three copies of segments that are 1/5. They're not the same type, so we just cannot count on as in this situation. But FFEF tells us if you don't like 2/3, you can multiply the numerator and denominator by any whole number you like. And watch what I do and you'll catch on why I do this. And this is not the only way of doing it, but this way works and you'll see why. So instead of 2/3, I'm going to replace 2/3 with the following. I'm going to multiply top and bottom numerator and denominator, by the same non-zero whole number. I can pick lots of numbers, but I'm going to tell you which one will always work. For this fraction, pick this denominator, and you'll see why in just a minute. So I pick 5 and 5. And same thing, 3 over 5. I'm going to apply FFEF one more time. I'll write 3/5. I need to multiply numerator and denominator by the same non-zero whole number. Can you guess what I might pick? Let's see. This 5 is this guy's denominator. What do you think I might pick? You're right. I'll pick this guy. Why? You'll see in just a minute what happens. When I do that, notice the denominator of this fraction is 15. The denominator of this fraction is also 15. How is that? Well, we arranged it that way. Or here the denominator was 3. I made sure the denominator was going to be 3 times 5. That's how I picked my 5 to multiply numerator and denominator. Here the denominator was 5. I made sure I picked this 3 and multiplied the numerator and denominator by 3. Then in the denominator I get 5 times 3, which is exactly the same as 3 times 5. That's why I get 15. What do I get in the numerator? 2 times 5 is 10. 3 times 3 is 9. What do I have now? I have 10 over 15 plus 9 over 15. What do we notice? 10 over 15 and 9 over 15 have the same denominator of 15. That means this problem is now exactly similar to these two problems, which is 10 copies of 115, 9 copies of 115. Now you really have 10 copies of something, 9 copies of the same type of thing. So we can simply add on, and I don't have space here, so I'm going to create space. 10 over 15 plus 9 over 15 equals 19 over 15. Now I can really apply the addition algorithm for adding fractions with the same denominator. That's what I did. And because these two fractions have a denominator of 15, when we add them, we get the same, another fraction of denominator 15. Numerator is just adding the two numerators, 10 and 9. Just counting on, because this time we have 10 copies of short segments of length 1/15, 9 copies of short segments of 1/15, 1 over 15. So now they're all the same size pieces. We can add them, and that's how we get it. So that's the moral of how we may add fractions with unlike denominators. All we do is we apply fundamental fact about equivalent fractions. We convert it into a fraction that works for us. Each one, we convert it into a fractions in such a way that the denominator is in fact the same, and we add it. So let's do a few more examples, and then we'll summarize once again using letters. Here's another example where we have two fractions with different denominators. And we proceed as before. We apply the fundamental fact about equivalent fractions, and in the following manner. 2 over 7, I replace it by an equivalent fraction. And fundamental fact tells you, you may multiply the numerator and denominator by any by the same non-zero whole number. And as before, we pick the denominator of the other guy, 10 for the same non-zero whole number. And for this one, 3 over 10, we replace it by an equivalent fraction. The fundamental fact about equivalent fractions tells us we may pick any non-zero whole number, the same one, we can put it here and here. And we pick 7, 7, and 7. What does that give us? Then we have 20 over 70 plus 21 over 70. So we replace 2 over 7 by its equivalent fraction, 20 over 70. We replace 3 over 10 by its equivalent fraction, 21 over 70. So Why is this sum a better one? Because now we have to add 20 copies of 1 over 70 and 21 copies of 1 over 70. These are fractions with the same denominator. And by applying the algorithm we have, we get a fraction with the same denominator. Numerator is simply adding the numerators. Here, we can simply add the numerators because the same denominator is telling us we have things of the same type, short segments of the same length. Here 20 of them, here 21 of them. Put them together, add them all up, just counting. So that's 20 and 21, added together is 41. And that's how we get that. Okay, so we've done a couple of examples with this same logic. Now, every problem I give you is going to proceed the same way, where if you notice the denominators are different, all you're going to do is you're going to say, okay, replace the first fraction by an equivalent fraction. The way you do it is apply FFEF, and the number you pick here will always be this denominator. And for this guy, the number you choose to multiply numerator and denominator, the same non-zero whole number, will always be the denominator of this guy. So we can summarize that using letters. So let's discuss this. So here I have, suppose A, B, C, D are whole numbers, and B is not equal to 0, D is not equal to 0. So what do I have here? A over B, a fraction, plus C over D, another fraction. Okay, just like this, but here we have now, by using letters, we give ourselves more freedom. If A could be 2, B could be 7, C could be 3, D could be 10, then we get exactly the same problem. But you could pick any other whole numbers for A, B, C, D, and then that means whatever we write out here also applies to another example. So let's see how we might proceed. Exactly the same way. We notice that two fractions have a different denominator. What do? We know how to add fractions with the same denominator, but we don't have that situation. So we go ahead and create for ourselves an equivalent fraction for A over B, another equivalent fraction for C over D, in such a way that the denominators exactly match up. How do we do that? We imitate this process. This one tells you A over B is replaced by A over B, and then they multiply the top and bottom by, do you guys remember what we did here? Where did we get the 10 from? From here. So here, what do you think we're going to pick? Right, we're going to pick D. There. Similarly, C and D, C over D, we multiply numerator and denominator. We can do so if F says by the same non-zero whole number. What are we going to pick? Let's look here. 3 over 10 times 7. Where did we get 7? 7 is the other guy's denominator. So here, C over D, we pick the other guy's denominator, B and B. Now notice what do we have? Same denominator, B times D, D times B, but you know, by the commutative law of multiplication, B times D is same as D times B. So no problem. What does that give us? That gives you, let me write it here. Same denominator. So I'll write the denominator as B times D. What's in the numerator? A times D. I'll put a parenthesis to keep it clean. Plus this number, which is C times B. So it's easiest if we can remember A over B plus C over D is this particular expression. What is this expression? How is it related to this? B times D is just these two numbers multiplied together. And and then in the numerator I have a plus sign. On the left side I have A times D. And then add it to C times B. That's what I have. So let's summarize this on the other word and put it together with the addition algorithm for fractions with like denominators. So we have everything in one place. Okay, let's read together what we have. Addition algorithms for adding fractions. So this is all the wisdom that we gathered from doing all of those examples. Suppose the letters A, B, C, D are whole numbers, and furthermore, the letters B, the whole numbers you choose for b cannot be 0. That's what this symbol means. We write an equal sign, cross it off, means b cannot be 0. Same way d cannot be 0. Other than that, 0, you can choose any whole number. This one we already discussed before, a over b plus c over b. Here we have fractions with the same denominator, and we explained that we discussed before, if you try to add them, then it's same as getting a fraction with the same denominator b is b. The numerator is just adding the two numbers that are in the numerator, a plus b. This one was pretty clear from before. And remember the logic of it, the way we said was a over b is a copies of short segments of each of length of 1 over b. C over b is c copies of short segments, also each segment is of length 1 over b. So here we are adding things of the same type, namely lengths 1 over b segments. So that's why we could just add like that, a plus c. And this is a new one that we derived. Here we are adding fractions with unlike denominators, b and d. I use different letters, meaning the whole numbers you choose for b, d could be different. Here same letter means once you choose b as 10, let's say, then this is also 10. So here, that's what the letters are saying. And these guys cannot be 0. How do we get this expression? So this is something, since you've done a lot of examples where I explained it, and I explained how we get this, at this point you can memorize this equation, this algorithm. How do we get this sign? Look at this. Here, let me erase this and write it as b times d, which is easier for you to read. So, how do we get the denominator b times d? From here. So, whenever we have to add a over a fraction plus another fraction with unlike denominators, the answer is, the sum is another fraction whose denominator is simply to multiply these two denominators. What's in the numerator? Two things added together. The first thing is a times d. That's what goes in here. Add to it b times c. That's what goes in here. So if you remember these two algorithms, then addition of fractions becomes very simple. So let's do another example where we apply this algorithm, which is derived by applying fundamental fact about equivalent fractions. But then remembering this algorithm, like the way I explained, makes it very easy. So let me review that again. We have two fractions with unlike denominators. When you add them, you get another fraction. Denominator is simply these two guys multiplied together. Numerator has two things we need to add. What are the two things? A times d plus b times c. B times c. So this is the algorithm now I'm going to use to do another example for you. Okay, I have two fractions that I would like to add. 6 over 11 plus 2 over 5. Notice right away these are two fractions with unlike denominators. The denominator is not the same. So the first method I showed you was how we replace each one by an equivalent fraction. And then we used that logic, and we arrived at this addition algorithm. So this time I want to show you how to do this in slightly fewer steps, simply by applying this algorithm, which we derived by applying the fundamental fact about equivalent fractions. And so because we did the hard work and derived this algorithm, now the reward is we can apply this algorithm if we can remember it. And remember, I explained to you how to remember it. I'll remind you again. A over b plus c over d is another fraction whose denominator is just these guys multiplied together. Numerator is adding two things. These two multiplied together plus these two multiplied together. That's what I'm going to apply. So, add two fractions with unlike denominators to get another fraction whose denominator is multiply these guys together. What is that? 55. Numerator is what? Multiply these two guys together. 6 times 5 is 30. Plus, multiply these two guys together. 11 times 2 is 22. 22. What do we get? 55. 30 plus 22 is 52. And so there is this answer. There is the sum. 6 over 11 plus 2 over 5 is 52 over 55. That's what it is. Okay? So we've done a lot of things today. So let me quickly summarize all the things we've done. And I'll do the summary in a general setting. Let's look at this here. Suppose A, B, C, D are whole numbers. B is not 0, D is not 0. Other than that, you can pick any whole numbers you like for A, B, C, D. Just don't pick zeros in this position. Adding two fractions. What does that mean? Concept-wise, it means same as the same way we defined addition of two numbers, 2 and 3, which was take a segment of length 2, end to end, put another segment of length 3, and then the 2 plus 3 denotes the length of the long segment. Here also, concept-wise, it's the same thing. A over B plus C over D is the length of a very long segment, which is made up of two short segments. The first short segment is of length A over B. End to end, you attach to it another segment of C over D. The long segment you get, its length is A over B plus C over D. And you might ask, but I want to know the exact fraction that length represents. And then we did a lot of work, including applying fundamental fact about equivalent fractions, and we arrived at this algorithm. So whenever you want to add A over B plus C over D, two fractions like this with unlike denominators, the answer is going to be another fraction. Draw a long line. Denominator is simply these two guys multiplied together. Numerator is this guy, these two numbers multiplied together, plus these two numbers multiplied together. And then everything else is easy. 30 plus 22 is 52 over 55. So that's how you can apply this algorithm to add fractions with unlike denominators. Thank you.